Okay, new chapter. So now we're going to be talking more about um, probabilities of random variables. Um, so when the same chance process is repeated several times, we are often interested in whether a particular outcome will or will not happen on each repetition. So, some examples of that might be to test whether someone has extrasensory perception or ESP. Um, we would choose one of four cards at random: a star, wave, cross, or circle. Ask the person to identify the card without seeing it. It's kind of like Ghostbusters, the original. Do this total of 50 times and see how many cards the person identifies correctly. The chance process here would be choose a card at random. The outcome of interest would be if the person identifies the card correctly. The random variable here, of course, would be the number of correct identifications, kind of similar to our taste test. Okay. A shipping company claims that 90% of its shipments arrive on time. To test this claim, take a random sample of 100 shipments made by the company last month and see how many actually did arrive on time. Chance process here would be randomly selecting a shipment and check it when it arrived. The outcome of interest, of course, would be arriving on time. And then the random variable here would be the number of shipments that did arrive on time. And then finally, something like a pass the pigs game. A player rolls a pair of pig-shaped die. On each roll, the player earns points according to how the pigs land. If the player gets a pig out, in which the two pigs land on opposite sides, she loses all points earned in that round, and then she must pass the pigs to the next player. A player can choose to stop rolling at any point during her turn and keep the points that she has earned before passing the pigs. The chance process here is rolling the pig dice. The outcome of interest would be the pig out. Random variable here would be the number of rolls until the player pigs out. Okay, so some random variables like x and y in the first two examples here would count the number of times the outcome of interest occurs in a fixed number of repetitions. That would be called a binomial random variable. So the binomial random variable is coming from a fixed number of repetitions. Okay, so we're only choosing the cards 50 times. We're only taking a sample of 100 shipments. The other random variables like T in the pass the pig setting, that counted the number of repetitions of the chance process it took for the outcome of interest to actually happen. So they're actually doing something, they're repeating something until they get the outcome that they wanted. So it's not a set number of repetitions, they're doing it until they get what they want. So that would be known as a geometric random variable. We're going to start our focus on binomial random variable. We'll talk more about geometric in either later videos, or I'm thinking we're probably just going to talk about it in class. So both of these would be discrete random variables. Okay. So let's look at these three situations and see if we can figure out what they all have in common. So if I toss a coin 5 times and I count the number of heads, I spin a roulette wheel 8 times and record how many times the ball lands in a slot. I take a random sample of 100 babies born in the U.S. Today, count the number of females. In each of these cases, we're performing repeated trials of the same process, same chance process. The number of trials is fixed in advance. Also, knowing the outcome of one trial tells us nothing about the outcome of any other trial. So, tossing a coin 5 times, you toss a coin once, it doesn't tell you what's going to happen the second time. Remember, these things have no memory. So that, in other words, would mean that these are obviously all independent events. We're interested in the number of times that a specific event, we'll call it a success, would actually occur. Our chances of getting a success are the same on each trial. So in the first one, the success would be a head. In the second one, a success would be a red slot. In the third one, my success would be a female. When these conditions are all met, we would have a binomial setting. Okay, so a binomial setting arises when we perform several independent trials of the same chance process, like flipping a coin 5 times, choosing 100 babies born today, and we'll record the number of times that a particular outcome occurs. We'll call that our success. So like the heads on a coin, a red slot on a roulette table, or females in births of children. The four conditions of a binomial setting are whether they are binary. So the idea that the possible outcomes of each trial can be classified as a success or a failure. So a heads is a success, failure then would be tails. Heads would be, success would be female, the failure would be male. Are they independent? Trials have to be independent of each other. That is, knowing the result of one trial must not have any effect on the other trial. So you can't have a situation where you remove cards and you don't put them back in. These have to all be independent of each other. The birth of one child doesn't affect what the next child's gender will be. The flip of one coin won't affect the other. These things don't remember what happened before, if you think of it that way. Okay, they have to have the number of trials that are fixed. So I had 100 or 100 babies born. I had 5 flips of a coin, and then it was 8. I think we spun the roulette wheel 8 times. These are all fixed numbers. We're not doing it any more than 5 times flipping a coin. We're not looking at any more than 100 babies born. We're not looking at any more than 8 spins on a roulette table. And finally, success. On each trial, the probability of success has to be the same. So the probability of success of flipping a heads on a coin is always the same. It's always a half or 1 out of 2 every time you flip a coin, okay? Same with the 100 babies born, okay? The probability of success would be the probability of getting a female. It's the same every time. It's always 1 out of 2, either a female or a male, okay? The roulette table would be the same. I think it's 18 reds out of, 38 spaces, okay? It's the same every time, okay? So a nice way of checking whether settings are binomial or not is to check all of these 4, but check bin. So we'll always say B, binary, I, N, S. So if we go down and it meets all 4 conditions, then we could say that it's a binomial setting, and we could carry on with whatever calculations that we may need later on down the line. Okay, so consider tossing a coin n times. So we already talked about all of this, okay? The count x of successes in a binomial setting is a binomial random variable. The probability distribution of x is a binomial distribution with parameters n and p. So n is going to be the number of trials, and p is going to be that probability of a success that doesn't change on any given trial. The possible values of x are the whole numbers from 0 to n. Okay. Note, when checking the binomial condition, be sure to check bins and make sure that you're being asked to count the number of successes in a certain number of trials. So what is the probability that you will have 3 heads in 5 trials? Okay. So here are three situations that we're going to see. We're going to look for whether it meets the criteria, the BINS conditions. Okay. So so the first one is genetics says that children receive genes from each of their parents independently. Each child of a particular set of parents has a probability of 0.25 of having type O blood. Suppose these parents have 5 children. Let X be the number of children with type O blood. Okay, so let's look to see if this is a binary setting or not. Okay, so the first thing is it binary? So the bins I'm checking right now. So the B is binary. Is it binary? So there I'm looking for, does it have a success and a failure situation? And it does. The success here would be that the child has type O blood. So the failure here would obviously be that the child doesn't have type O blood. Are they independent? Well, yes, they are. One, they tell you in the problem, but also knowing one child's blood type tells you nothing about another's. Children will inherit genes determining their blood type independently from each of their parents. It says that in the very first sentence of the situation. Okay, now we're looking for the N, so number, okay? Are there a fixed number of trials in this situation? Yes, there are. They said, suppose the parents have 5 children. They're stopping it at 5, okay? So the 5 is fixing it, so we're good there. We have N is equal to 5 trials in this chance process. And then finally, success. So, is the probability of success, which is that the child has type O blood, is that going to be the same for every one of the 5 children? And it is. It says each of the particular set of parents has a probability of 0.25 of having type O blood. That means the probability of success is 0.25 on every trial. So it meets BINS. It qualifies on each 4 of our 4 conditions, and so this would definitely be a binary setting. Let's take a look at another one. So we're going to shuffle a deck of cards. We're going to turn over the first 10 cards one at a time. We're going to let y equal the random variable y equal the number of aces that we observe. Okay, so we're going to go ahead and we're going to check BINS again. So B would be if it's binary. Let me see if I could just write a little bit here. Okay, so we're looking to see if it's binary. Okay, does it have a success and a failure? Okay, and it does. Okay, the success here would be getting an ace. Okay, and the fail here. Okay, the failure here would be just not an ace. Okay, are they independent? And this is where we could pretty much stop because they're not independent. We know that we're flipping over the first 10 cards, okay? That means that your probabilities are going to change for each new card you flip over. Okay, you're turning over the first 10 cards. You're not turning over one, putting it back, shuffling, and then flipping over another one, putting it back, shuffling, taking over another one, and doing that 10 times. You're just flipping over the top 10 cards, which means after you flip over the one card, you now have one less total, and you also have one less of that specific card. So they're definitely not independent here. So right away we know that checking BINS, the independent, it doesn't work. So this would not be a binary setting, okay? So let's go down to the next problem. So shuffle a deck of cards, turn over the top card, put the card back in the deck, and now we're going to shuffle again. So this would kind of satisfy the situation that wasn't satisfied in the top problem, okay? Because like I said, now we're going to shuffle, we're going to turn it over, we're going to put it back, we're going to shuffle again, okay? So the idea of independent would work here. Okay, we're going to repeat this process until we get an ace. and we'll let the random variable W represent the number of cards required, okay? So the first thing is binary. So it's much like the first the situation out on top here. It would be binary. There is a success and there's a failure, so it's the same as the last time. Success would be getting an ace, failure would be not getting an ace. Independent, we're replacing the cards this time, so we fulfill that need, right? So we're good there. It is independent. Every time you replace it, it doesn't affect what you're going to choose next. The number of trials, however, is not fixed. We're turning these over until we get an ace, okay? That can happen, on the first 10. It can happen several times down the line, but we're not just doing this 10 times. We're not just flipping over 15 cards. We're not just flipping over 12 cards. We're doing this until we get an ace. So we're repeating the process until we get a success. It's not a fixed number of trials, and so this would not be a binary setting. So in the first, looking at these, the only one that was a binary setting was the first one. The second one was an independent, and the third one did not have a fixed number of trials. Okay, and that is it for this video.